So we're very happy to have Professor Erkki Somersalo from Case Western Reserve University, and he will speak on probabilistic inverse problems. And as far as I know, Erkki, I've been to India at least a couple of times. So anyway, so we could not meet in person this time, but hopefully very soon. So over to you, Professor Erkki Somersalo.
Thank you. Thanks for the invitation and for the possibility to give this presentation. As Venki mentioned, I have been in Bangalore visiting the institute, and it was really a pleasant visit, and I hope that I can do that again soon. Okay, so my talk is following what Daniela started yesterday on probabilistic inverse problems. So we are talking about Bayesian methods. I'm trying to get my, all right, so here we go. So we are going to look at today on time-dependent problems. And so there's a little bit of history that I want to mention here. So the time-dependent problems have been there, or time-dependent ideas in Bayesian framework have been there from the very beginning of the Bayesian methodology. So as early as 1764, after Bayes' essay on probability, Richard Price, who was a Welsh philosopher, was writing an essay on the probability of the sunrise, which sounds kind of silly, but the idea is that when we are witnessing sunrise, our expectation of seeing another sunrise will increase. And so he was interested how this expectation changes from day to day based on the experience. And so Pierre-Simon Laplace, who is one of the names who really developed the Bayesian theory as we know it today, wrote 10 years later another article, and there's a famous article by Buffon, who's a probabilist who was dealing with the same issue. And so so the idea is that the probability here in the Bayesian framework is simply referring to our expectation. And so the idea is that what these old references were sort of looking at was how the expectation changes from experience to experience. So there is a nice discussion of this idea in Nate Silver's best-selling book, The Signal and the Noise, where the author is discussing the 911 attacks. And so he explains how for the first time we saw the plane crash on a skyscraper, we thought that it could have been an accident. When the second plane came, nobody thought that it was an accident. So we had updated our expectations. So that was the idea. And so if you read that book, you see a little bit of the same argument put in numbers. So it is quite interesting. But so we are talking about something more specific here, so not attacks. And in general, so dynamic inverse problems. So I'm trying to frame it first a little bit theoretically, and so then we look at a simple example which somehow explains the basic ideas, and then we return back to this formalism. So what we do, we assume that we have discrete time 0, 1, 2. You can think that this t is measuring time in, let's say, days or weeks. And so every day or every week something happens, like the sunrise. So xt is the time-dependent random variables or stochastic process. So in this original idea, xt could be the sunrise. So 1 means sun is rising, 0 means sun is not rising. And so then we have an observation. So we are going and look at something. So we define bt as an observation. So in the sunrise question, bt could be directly the observation of the sunrise itself. Usually we have error in our observation. So what could error mean in the sunrise example? Maybe you have clouds or mountains and you don't really know if the sun was rising, but you believe that it is because the light is coming. So that should somehow represent the error here. And so then we have the prior information, which is expressing what we believe before the observation. So when we go and see the sunrise, we already have a prior idea And so we express, well, sun came up yesterday and the day before, so I'm expecting it to rise today. And so you give a higher probability for the positive occurrence than for the negative. So that's the prior. And so then if you look at the inverse problem, so the inverse problem is that we are going to update the model or the probability density based on all previous observations. So BT is the accumulation of all observations. So that's the basic idea. And so how do we do this in the Bayesian framework? So that is the question. So I'm starting with a very simple example, and this is something that an Italian colleague of ours once mentioned. He's a Bayesian statistician, and so he gave this nice idea to us to look at. So the idea is that you are looking, you're trying to locate a hunter who is walking in the forest. You don't know where the hunter is, so you don't observe directly the hunter. You only know that the hunter has a certain speed at which he is walking in the forest, and the speed does not exceed a maximum speed, Vmax. Now, you know that the hunter starts at t equals 0 from home. So let's put that in the origin. So x is 0, 0. And we know that the hunter goes out with his dog, and the dog is a good dog, so it never runs too far away from the hunter. So the distance d, which is the distance between the hunter and the dog, is never larger than d max. This is an a priori assumption. We can then weaken this a little bit. We say, well, maybe because the dog is after all not in a leash, so we can say that it's within the distance d max with very high probability, but not necessarily with 100% probability. And so then the observation, we think that every now and then the dog appears. So we have the observations of the dog here and there, and so following the places where we have seen the dog, we are trying to infer on the position of the hunter based on this information. So the problem is to estimate the trajectory of the hunter. So that's the problem we're looking at. So what we are going to do here is so-called particle approach. And particle approach means that we are sort of generating plausible realizations of the trajectory or the positions of the hunter. And based on that, we are then assessing the position of the hunter. So at time step tj, when we are again going to encounter the dog, we are generating a sample of possible positions, x1, x2, etc., xn, and the super index is referring to the particle, so that's the computational realization of possible position of the hunter, and j is referring to time. And so let's see how we do this generation of those possible points step by step. So we start with t equals 0 or t equals t0. So you can think that t is 0 with the certainty that the hunter is at the origin. So what is the cloud of possible positions of the hunter in this case? Well, since we know that for certainty the hunter at time equals 0 is home, so therefore my particles x0, k are all located where home is, which is the origin. So I have n realizations, n computational models, so to speak, of this hunter, and in each realization the hunter is at home. And since there is no reason to believe that any of those particles is more important than others, I give each particle the same weight. So this W0K is referring to the importance of a particle. And so every particle is important, so the weight is 1 over n. So now we start to follow these particles. What happens when time moves on? So let's go to the first discrete time equals t1. Before we observe the dog, so we know that at t equals 1, the dog is going to appear. Okay, so what are our expectations of the position of the hunter before the dog is seen? Well, the idea is that we are propagating each one of those initial particles which were at home by adding a random step. So we are moving each particle randomly in the plane, which is now the map where we sort of model the position of the hunter. And I'm defining new particles, x hat. So this hat is sort of a proposal. Where could the hunter possibly be before the dog is being seen? And so what is the random step? So in order to fix how we use this random step, we have to use the a priori assumptions. So first of all, the random step cannot be larger than the maximum speed of the hunter times the time elapsed, which is t1 minus t0. So this is the maximum distance that the hunter could possibly walk. Decided to walk with maximum speed in a certain direction without changing direction. So that is the distance that the hunter cannot exceed when walking with his speed, which is limited by Vmax. So I fixed this gamma 1. And so then I don't know where the hunter is going, which direction he's going. So in this case, we assume that the terrain is such that there is no preferential directions. We don't maybe know about the terrain, or we assume that it's all flat or equally difficult to walk. So we have no preferential direction. And so therefore what we do here, we draw first the direction of the hunter. So we give each particle possibility to move in any direction with angle from 0 to 2 pi. So we draw this theta from uniform distribution between 0 and pi. Then we define a unit vector cosine theta sine theta. So that is pointing in the direction where the hunter moved. And then S is a random variable which is drawn from uniform distribution between 0 and 1, so that the length of my random vector W1 is always less than gamma 1. And so this is the random variable whose realizations is W1KR. So we are defining first the process, how we draw, and then we draw random steps. And so how does it look like? So here I'm using 5 particles, and in this plot, the black dot is home origin, and then I'm drawing 5 possibilities where the hunter might have gone. So x1 is 1. I realized that my notation is a little bit changing, so this parenthesis was not previously there. So x1 hat is the first possible position, x2 hat is the second possible position, etc. So I have 5 possible positions, and so this is before we see the dog. So these are possible realizations of the hunter's movement. Of course, in reality, if you want to do this, you have to use much more than 5 particles. So typically, people are using tens of thousands, hundreds of thousands, even millions of particles, depending on what we are modeling. But so for the sake of making this plot clear, I'm just following 5 particles so that you see what is going on. So this is the random propagation. So then the dog shows up. So for those of you who don't know what the dog is, so here it is. So the dog shows up, and so this red square here is the place where we see the dog. Okay, and so then we know that the dog is never further away from the hunter than d max, and so therefore I draw a circle around the position of the dog, and that circle defines a disk, which is here in blue. And so the possible positions of the hunter are within this disk, because otherwise the dog would be further away from the hunter. So what does this drawing tell me? It tells me that when I did the simulation of the trajectory of the hunter, so x1 and x3 were simulations that fell into this disk, and so these are possible simulations, while x2, x4, and x5 are simulations that are not possible. They are not in line with the data and with the assumption. So when I move on, I have to discard all the possible realizations which are not within this disk. Only those two realizations are possible. Okay, so that's the picture. Here is what it means in terms of formula. So B1 is the position of the dog at T1. And in general, it's a random variable, since I don't know in advance what is happening. So, and B1 is the realization. So B1 is the one that we observe. B1 lowercase is the one that we observe. That's the red square here. What is the likelihood? So likelihood tells you, if you would know the position of the hunter X1, what is the distribution of B1, the position of the dog. So this is the likelihood by definition. In this case, we are using the characteristic function or indicator function of a disk centered at X1, position of the hunter, and radius d max. So here you see that we are in my plot, I was using the disk where the dog was, but when we are defining the likelihood, I have to define the probability of the position of the dog given the position of the hunter. So this is how Bayes' formula works. And so D is the disk. So we take the characteristic function. Of course, if you look at this characteristic function as a function of two variables, X1 and B1, so we define this function thinking that we know X1 and see where B1 is. But in reality, we are observing B1 and we are looking for X1. So we are interpreting in our Bayes formula this function as a function of X1 given B1. And so therefore, I was drawing this picture. B was given and X was the unknown. But the function is defined itself in the other order. That's how likelihood works. So what we do now, we say, well, which ones of those particles are important? So we are assigning a weight to each particle. And clearly, and so we do this by using the likelihood. So as I said, I give a big importance to the particles which are possible, which are inside the disk. So I'm evaluating this likelihood function given the position of the dog. And so what this weight function does is that it assigns zero importance to the realizations of the hunter in positions which are not possible, given that the dog was seen at that red square. So here's the dog, and so you have different realizations. All these people could be realization. So you are only given big weight to those people who are sort of close to the hunter, and not to the ones who are too far away. So this is the idea. So now what we have the realizations of the possible positions of the hunters, and we have attached an importance weight for those. And so then what we do is in this introductory example, so we pick out of those possible realizations according to their importance weight. So what is the probability that xj hat will be picked? The probability, the relative chance of being picked is this weight. So we are drawing without replacement, with replacement from this set. So we are picking, let's say, if you want to have 5 realizations of your hunter's position, you are picking 5 particles out of this set by sampling with replacement 5 times from this set using the weights W1, W2, etc., Wn. And so then you have the new sample and then you move on. So how does it look like in this case? Well, I had only 2 possibilities, 2 particles that had a positive weight. The others were not possible, they had 0 weight. So when I do this sampling with replacement, what happens is that my 5 particles will be drawn among those 2 possibilities. So in this case, I have got X1 and X2 to be equal to this particle, X1, X3, X4, and X5 to be that other particle. So now I have 3 replicas of this position and 2 replicas of that position. And so those are my new particles. And then I move on with these. So the idea is rather clear. As you can see, So when we are estimating the hunter's position, we don't know where the hunter is at T1. So what we do, we take the average of those positions. And so in this case, the hunter's position would be, since I have 3 replicas of this and 2 replicas of that, so it is on the line between these 2 points, a little bit closer to the heavier point where I have more samples. So that's the idea, and so then we repeat the process and we move on. So that's the basic idea of particle filters. Now, what could go wrong here? So first of all, we saw that first I had 5 nice spread out particles here, and when the observation came, my selection of possible positions was reduced to 2. So there's something which is called a sort of data thinning or sample impoverishment going on here. So we sort of are throwing away lots of samples, and we are sort of representing the possible positions of the hunter with less and less different points. So that's called data thinning or sample impoverishment. So we have repetitions of the same particle. So that's not nice. We are trying to see that how to avoid that later. And so when you ask about the uncertainty of the position of the hunter, so you saw that in my example, the uncertainty was reduced to 1 line. So I had only 2 possibilities, and the possible position of the hunter is somewhere on the line between those 2 points. And so that doesn't really give me an idea what the spread is of my uncertainty. So the impoverishment does not reflect well the uncertainty that I have about the position of the hunter. And so first of all, in this example, it's possible that we lose all particles. So I was lucky to have 2 particles inside this disk. But what if my random points were such that no particles were falling in the disk where the dog shows up? Well, then I'm in trouble, because then I'm losing all the particles and my algorithm stops. So that's another thing that we need to worry about. So one fix for the last problem was that we were using a likelihood that was really harsh. So it was 1, 0. So either you're inside the disk or outside the disk, which is reflecting some sort of overwhelming confidence about the dog. The dog, after all, is not on the leash. So what we can do here, we can make a little bit softer likelihood by saying that first of all, we can say that the hunter may run, sometimes go a little bit faster than what we thought. So instead of using this absolute maximum distance that the hunter can travel, we could use, for instance, a Gaussian distribution. So then we say that the hunter is within the disk of radius gamma 1 with high probability. The same thing with the dog. So we can say that, well, the dog is not further away from the hunter than this D max, which I for some reason call D0 here, but so we can use a Gaussian. So maybe the dog sees a rabbit and runs a little bit faster than expected and forgets to think about the hunter, and so maybe it can be a little bit further away than this D max. And so we can use a Gaussian likelihood, and that makes it possible that the weights, they can be small, but they are never 0. So I'm not losing completely my particles, and that's a good thing. So the particles are there, they may have very low probability, but the probability is not 0. And so when I'm calculating the weights, I get some particles always which have higher probabilities than others, and so I can always draw some particles. That's not necessarily a fix for the data impoverishment, but that already helps. And so this process, if you want, so suppose I have this x hat x. So when we do this random draw, so we are selecting the particles that we are using the weights W. So this process is called importance resampling. And so we did, in our hunter example, we did an importance resampling. So we generated first the particles with weights, and then we selected new particles from this set with replacement, and that is called importance resampling. And so, okay, so in this, let me see. So the weights, so this is incorrect. I had to correct it. So the weights are not equal, but if they were equal, so then well, forget about this. So so what I wanted to say is that the process is called importance resampling. So when we do this more systematically, so now let's move on and let's try to make a little bit more mathematics out of it and do this more systematically. We need to know how to approximate densities. So I'm starting with something which is probably familiar with everybody, namely the law of large numbers. And law of large numbers says that if I have independent samples of a random variable, so I have a random variable which has a distribution pi of x, and then I'm sampling independently from this distribution, I get x1, etc., xn. And so if I'm asking what is the expectation of the value of a function evaluated at those points. So this is elementary descriptive statistics that we take the mean of those values. So if all points are equally probable, then the expectation is typically characterized by calculating the mean value of them. And so when you increase n, so you have more and more samples, the law of large numbers says that this average is indeed converging to the expectation of f of x. I can write this convergence statement here, which is very intuitive in terms of the probability densities. So let's use Dirac deltas. So Dirac deltas are point masses that are sitting at points xj. And I have endpoints. And so I'm putting point masses at those locations. And then I'm defining a sum of those point masses. And so this is a probability density. And what does this probability density do? It evaluates my function f at those points xj. So f here is a continuous function. So if I do the point evaluation of my function fx at points xj, I get the left-hand side of the formula above. On the other hand, the expectation is an integral of f of x with respect to the probability density of the random variable x. So this is how the probability density defines expectation of a function f of x. And so what I have written here in terms of the law of large numbers is simply that this integral with the discrete measure is converging to the integral with the continuous measure. And so this is often expressed by saying that the discrete measure converges to the continuous measure in the weak star sense. And what does this weak star mean? It means exactly what you see in the row above. So for all continuous functions, this integral on the left converges to the integral on the right. So that's another way of saying the same thing. What is important here is that once you have decided in which sense this discrete measure is approximating your continuous measure, you can say, well, I can write that my pi of x is approximately the discrete measure. So if I have weights which are not equal, so if I don't have 1 over n, but I have some weights wj, the previous formula was written in terms of those weights, where the weights are such that they all sum to 1. And so this gives me the reason to write that pi of x is approximately the discrete measure. And the higher this n is, the closer these two measures are in the weak sense. And so therefore, this approximation has to be understood in this sense. So when I'm writing this approximation, I mean that when I integrate it against a continuous function, the numbers are close to each other. And so this is called the sample-based approximation of pi of x. Now we go to what is known as Markov model. So we are writing a time evolution. So we have this sequence of random variables, xj. And so I'm writing a model saying that the next random variable depends on the previous one. And it depends on the history only through the previous x. And then there is some random innovation or uncertainty in the model. So I'm not looking at the completely deterministic model, but somehow model that has a little bit of uncertainty. I have an observation model, so my random variable bj is a function of my xj, and then there's observation error. So this is the evolution model, and this is the observation model. And so using those two models, I should be able to write a particle algorithm that is following what is happening with my belief where my x is. And so here is the schematic idea. So why I start with the current probability density. So xj given all the accumulated observations b1 to bj. So what I'm doing, I'm using the evolution model to update my distribution. So I make a prediction of my xj plus 1s, and then the new observation comes, I make a correction. So I'm updating my density so that I'm adding the last observation. So 2 steps, prediction, correction. So these 2 steps are often called propagation step and analysis step. And so in this slide, which looks very complicated, I have shown 2 formulas, and I'm going a little bit through these. But first, let me show. So the first one is often referred to the Chapman-Kolmogorov formula, which is telling how the updating goes. And the second formula is nothing else but Bayes' formula, and that tells how I'm going to use the latest data. And so then I'm combining them, and I have one single formula that I'm going to use. So rather than going through this complicated slide, I'm simplifying a little bit the notation. So in order to make this a little bit readable, I'm leaving out these sub-indices here, telling which probability density random variable we are talking about. I'm only keeping what is in the variable part. So the same slide with a little bit simplified, lighter notation. So now we can look at this. So the probability density of xj plus 1 given all observations to time tj. So remember, d is the accumulation of observations, is an integral of the conditional probability of xj plus 1 given xj times the probability density of xj given the observations, and then integrate it out. And I'm deriving this formula for you in the next slide. So this is the Chapman-Kolmogorov formula. Bayes' formula instead says that the estimate or the distribution of xj plus 1 given all my observations up to time t j plus 1 is the probability density of xj plus 1 given the previous observation times the likelihood. So you see that this is really like Bayes' formula. So here is my prior. My prior is telling what I believe that the position is without seeing the latest observation. So this is my prior. And the update of my prior comes from with the likelihood. So now I'm using the likelihood. What is the likelihood of the position bj plus 1, assuming that my position is xj plus 1. And so when I'm multiplying, so I'm plugging in this Chapman-Kolmogorov formula here, I get this formula here, which is the updating formula that the particle filtering algorithms are based on. So let me go through this Chapman-Kolmogorov formula so that you see where it came from. So what I was using here, it was that the joint probability distribution of xj plus 1 and xj is simply using the formula of combining probabilities. It is the probability of xj times the probability of xj plus 1 given xj. So this is almost the definition of the conditional probability, right? So dividing by pi of j, you can see that this is the definition of the conditional probability. So I'm starting with that. Now, if I'm only interested in xj plus 1 and not of xj, what should I do? I should marginalize. So I should integrate out the variable that I'm not interested in, which is xj. So I'm taking integral of that formula, and I get this formula integral of xj plus 1 given xj times the probability of xj. Now you write the whole formula conditional on dj, so the previous observation, and you have the Chapman-Kolmogorov formula. So let's see. Remember this formula, and let's go back. Yes, indeed. So I'm writing all the distributions only using the fact that all the distributions are conditional on my previous observations, and I have this formula. So this is how you derive simply the Chapman-Kolmogorov formula. So these are the two things that you need to know: Chapman-Kolmogorov and Bayes formula. Okay, so let's go and see now again what we are supposed to do here. So we have the sample of the possible positions of the hunter at time j, and every observation has its weight, importance weight W1j. Okay, so I'll take this combined formula. So here's Chapman-Kolmogorov, and here is the likelihood. And what I'm doing is that I'm replacing this pi of j given dj with a discrete approximation of that measure. So I don't know this distribution pi xj given dj, but I have a sample of points which are presumably drawn out of that probability distribution. So I'm using the discrete approximation, and I'm plugging it in here. So remember, when you are using point masses simply mean that you do point evaluation. So the continuous function that we are looking at is this f of xj is this one here. And so I'm only evaluating my function pi at those points. And so this is my new operating formula, which is based completely on the previous sample. And so what I have to do now is to devise an algorithm that draws a new sample from this probability distribution. So this looks doable, right? Because first of all, notice that this part here, here's the formula. So first of all, the second distribution here depends only on the propagation model, and the first distribution is its likelihood, and it depends only on the observation model. So we have the propagation and observation separated in this formula. And what we did in the previous example is that we took the likelihood and we drew the weights, the importance weights from the likelihood, and then we just resample. So that was the idea. So here is the formula here is the algorithm that we were using. It is called sampling importance resampling, and I'm going through this based on that formula, and then I'm showing how this was used in the hunter and the dog example. So first of all, we are at point t equals j in time. So we draw the candidate particles from the propagation formula. So here is the formula. So we are drawing new candidate particles from this propagation model. So from here. And then we calculate the relative likelihoods. That's what we did in the hunter and the dog case. So the dog shows up, so bj plus 1 is given. So then we are asking what are the likelihoods of the propagated points. And in this case, I have to include also the weight. Then I normalize these weights because these are probability weights, and the sum has to be 1. So I'm normalizing these g's. And then I do a resampling with replacement. So now I have the probabilities, and I'm drawing new particles from this set using these weights. So that was exactly what we did in the dog and the hunter example. And so now you have a general idea how you would implement the sampling importance resampling algorithm. This is what we used in the hunter and the dog example. Now, I mentioned that we are easily losing particles, and so there's this particle impoverishment. So let's try to make a remedy. So what I'm doing is the following, and then I show graphically what is going on here. So I'm changing a little bit of the strategy now. So first of all, I have these previous positions of the hunter, the previous possible position of the hunter. What I'm doing, I'm propagating, but not adding the random noise here. So I'm just propagating using what f is, which is sort of a deterministic Markov model. So then I'm taking my fundamental formula, I'm moving the likelihood in, so here's the likelihood, inside this sum, and then I'm multiplying and dividing by the likelihood evaluated at these propagated points. And so now I have a little bit more complicated looking formula. And so I'm going to consider this GNJ plus 1, which is the likelihood times the weight, as a predictor how well the auxiliary particle would explain the data. So if that's the likelihood likelihood of the propagated particle, if we wouldn't have, you know, the random component there. So what I consider this GN to be, it is sort of the fitness of my XJN particle, in the sense that I'm asking how well, if I had no randomness in my propagation model, how well that particle would be able to explain the next data. And so then what I can do, I can sample my new positions using these importance weights. So I'm drawing the new particles from this propagation model, and then I'm recalculating the weights of those. And that's the strategy which leads me to an algorithm which I call survival of the fittest. And so the idea is really that we are first looking which ones of those particles were sort of fit enough to explain the data, and then we are generating the particles. So here is the survival of the fittest. So we start with the initial position of the hunter. So W's are all equal, and we know that the hunter is at home. So pi 0 is just the delta distribution at the origin in our case. Now what we do is we first propagate. So now we are at the jth time step. So what I'm doing, suppose I have those jth positions. So I'm propagating using the deterministic model. And so then I'm calculating the fitness weight. So I'm asking how well the propagated particles would be able to explain the next data point. So these are the fitness weights. And then I'm sampling from my particle cloud. I'm sampling the old particles using these fitness weights as probability weights. And to make the renumbering linear again, so I'm drawing these indices Ln, and then I'm renaming the particles according to those indices. So B and C put together means that you are sort of drawing from your urn of the old particles new particles with replacement using these fitness weights as their probabilities. And once you have that, you add the random step to those propagated particles. Remember, after all, my Markov model was not deterministic, it was probabilistic, so there was an innovation. So I'm propagating with randomness, and then I'm recalculating the weight. So I'm asking, well, I only know how well the parent particle X bar was able to explain the data, but I'm really interested how well the offspring particle is able to explain the data. So I have to update the weights by taking the ratio of those likelihoods. And then, of course, since I want them to be probability weights, I have to normalize, and then you repeat. So let me show with this particular example of the dog and the hunter how this works. So you see the difference. So in the preliminary example, we used a random walk model. So xj plus 1 was xj plus a random step. So what does it mean? It means that this f is identity. So my Markov model is such that my f is identity. And so therefore, what are the predictors? The predictors are the old points, because it's identity. I'm not moving them anywhere, so I'm just keeping them where they are. And so now I'm asking, what is the likelihood of these old points to explain the new position of the dog? And so that's the fitness weight. So I'm giving more possibility to particles which are better to explain the next position of the dog. I give more weight for those. So here's a pixel description. So my initial, so the first row here is the sampling importance resampling. The second row represents survival of the fittest. So let's see how this works. So the black dots in this first panel, they are the positions X, J of the hunter. So these are my particles in the previous round. So in the sampling importance resampling, I'm propagating every particle using the propagation model. So in this case, I'm taking the identity plus a random step. And so the green points are where all these particles would end up. And so now I have these X hats, which are the green dots. Then I'm assigning to each one of those green dots the importance weight using the likelihood, and then I'm resampling. And so on this slide here, on this panel here, you see the red square is of course the dog here. So so you see these green points, and those green points are what I have after the resampling. And so you see that I have only 4 points left, and there's one point which is more important than the others. And obviously in this case of these 4 points, this point which is smallest is the least important. So I have resampled here this big green square several times, and I'm implicating this, indicating the fact that this green square was sampled several times by drawing this square a little bit larger than the other ones. And so that would be my outcome in sampling importance resampling. So first you propagate everybody, then you ask the importance, and then you resample. Now I go to the survival of the fittest. So what I do is I first give each parent particle, which are these black dots, a possibility to proliferate. But the possibility or the probability for them to proliferate depends on how well they are able to explain the next data. And so you see that there are some particles which are not able to explain the data at all. So they were never selected. So the survival of the fittest was selecting, in this case, only 1, 2, 3 particles. So only 3 particles were selected to proliferate. And then I'm adding the random step. So now I'm adding the random step to those 3 particles which have selected several times. And so, for instance, this particle was selected 4 times, so it has the right to create 4 offsprings. This particle was selected 2 times, so it has the right to generate 2 offsprings, etc. So you see that the offspring generation in this case is taking place closer to the next appearance of the dog compared to this SIR, which is letting the offsprings to be way off the next data. And so when I do the resampling, I get these green points here. And so now I'm resampling only among these yellow points. Well, the fundamental difference here is, although I see that in this case I get only 4 points, and here I get 5 points, so it looks like different points. It looks like the impoverishment is still taking place. Well, there's always a little bit of impoverishment in these particle filters. I'm looking here at 10 particles, so the difference between 4 and 5 is already sort of significant, although not that significant. If you go to higher particle counts, you will see really a big difference. The more important thing is that the points that I had in this case, in the survival of the fittest, they are representing better my uncertainty of where the hunter could be. So think about this upper panel. So where would you put the hunter in this case? You would put it in the center of mass of these points here, which would be somewhere in this dark gray area. And that's not really reflecting your model, because you know that the hunter should be sort of close to the dog. Whereas if I'm calculating the position of the hunter using my survival of the fittest particles, the approximation is closer to the dog. Of course, I don't know in this case where the hunter is, so I cannot tell what is the correct answer. But I assume that in the lower example, my approximation is sort of satisfying better the likelihood requirement. Now, there is an extension to this when you have parameters in your model, and that's often of interest. So you may have some parameters, for instance, in your suppose your propagation is based on ordinary differential equations, for instance, as in a model, in an example that I'm going to show you later, it is the case. So you may have some unknown parameters, and you want to often estimate those parameters as well, not only the state that you are following. And so how do you do that? Well, often you know that the parameters are static, so they are not evolving in time. So what I'm doing, I'm taking the formula combining Chapman-Kolmogorov and Bayes formula, but I'm writing everything including the parameter theta. And so notice I'm writing this theta as if it were time dependent. So there is this sub-index j here. Well, the idea is that although I assume that my parameter is not time dependent, my information about that parameter is time dependent. And so when I'm expressing what I know at time t equals j about that parameter, I have to use the concept of probability distribution. My probability distribution is encoded in the sample. And so therefore, since my information about the parameter is changing with time as well, so I'm using a time-dependent model for the parameter, although I'm assuming that it is not time-dependent. Now, the parameters are included into the model, for instance, using something which is known as a Gaussian mixture model. It's a very handy way of including those. So what I'm saying is that suppose I have the cloud theta j from 1 to n, and I would like to draw a next approximation for my parameter. So how do I do this drawing? So if I draw from the point mass formula of theta, I'm always repeating the same value of the parameter because point masses are living on those points that I know. So what I'm doing, I'm putting around each point a small Gaussian. So what I'm doing here, I'm taking the mean value of my current parameter values. I'm calculating the covariance matrix, empirical covariance matrix based on the cloud. And then I'm drawing a small Gaussian probability distribution around each point by taking this covariance matrix C and scaling it down with a small parameter. So you can think that I'm putting a small Gaussian instead of a point mass where I have those points. And so now it's easy to draw the next guess for this theta. So I'm using this model to propagate my particles. So I don't have a propagation model for my particles, which are the parameters, because I'm thinking that the parameters are constant. So there's no natural propagation model for them. In order to do this propagation, I have to have a probability distribution from which to draw. And so in order to avoid this impoverishment, so that I'm not always drawing the same value of the parameter from smaller and smaller distribution, selection of particles, I put these little Gaussians around them. So from this Gaussian distribution, it's rather simple to draw a new guess. And so what is the problem with this? Well, if you go and calculate the covariance of this model, this sum of little Gaussians, you do the calculation and you realize that the covariance of j plus 1 is slightly larger than the covariance, the empirical covariance of the previous particle, theta j. This is not good because I said that my theta should be static. So when I'm doing the propagation, the uncertainty should not increase. There's no reason to go and increase the uncertainty of the particles when we are doing the propagation. There's nothing that increases the uncertainty. The certainty is what it is. And so therefore I make a small correction. So what I'm doing, I'm taking the old particles and I'm moving them a little bit towards the sample mean. So I'm taking a convex combination of the sample mean and the particle, take a line between those 2 points and move it a little bit towards the center. And then define a new Gaussian mixture. Now the little Gaussians are centered not on the original position of the particles, but in this point, which is moved slightly towards this center of mass. How much are we moving those points? If you choose the parameter A controlling this movement to be 1 over square root of 1 minus h squared, if you do the calculation, you realize that this Gaussian mixture model has exactly the same covariance, C, as you had with the previous one. So this is a propagation model that does not deteriorate your information about the new position of the particle. And so this is often referred to as artificial diffusion that you are avoiding with this trick. And so I'm not going through these formulas here in detail because of the lack of time, but you will have all these slides. The basic idea is that we use the same survival of the fittest algorithm as we used before. The only thing is that we have to update our parameter also. So when we are doing the propagation, we are propagating xj using the propagation model that we have, and we are using this Gaussian mixture model to propagate our thetas. Otherwise, the formula is exactly the same, and so you get a nice survival of the fittest algorithm for parameter-dependent particles. And to close this presentation, I'm showing you some results only, not formulas, of an application where we use this particle filtering idea. This is a recent article that just came out in Inverse Problems, where we were looking at the spread of the COVID-19. So this was our pastime hobby during the lockdown days of the pandemic. So what we did, we were looking at the modification of the SEIR compartment model, where the population is divided into the cohorts. S is susceptible, I is infected, R is recovered, and then this E is exposed. We added something which is called asymptomatic, because COVID is characterized by people who are not really showing symptoms, and they are not quarantined, and they are going around. They behave like exposed, but they are spreading the virus. And so we combined those 2 compartments for reasons that I'm not going to explain in detail here. And so what we did, we took the daily count data. Daily count data means how many new cases. This is like observing the dog. So we are observing how many new cases you have each day of infected. And so we were applying this to the publicly available data in Cleveland area, and also in a larger areas in Ohio. And so what you are observing is a noisy realization of this phi2, which is the rate at which people get infected. And so here are some of the latest predictions or estimates of some parameters. So you see here is the daily count data from Cuyahoga County, which is the county where we are at in Cleveland. And so you see these blue bars are the daily count. So you see that there's a reporting error, because during the weekends they are not reporting the infected. They are always accumulating the weekend cases to the Monday count. So you see the Monday peaks, and then you see the holes in the weekend. So you could easily get rid of this oscillatory nature. But on the other hand, since we know what the artifact is, it doesn't really bother us. So these are the daily counts. The envelope here is calculated using our particle filter. And so this envelope is sort of giving us an estimate of the expected number of counts. And so here we see one thing that is important in COVID is to understand how much uninfected people there are out there compared to the infected people. So the ratio of uninfected divided by the infected. And so we see that this ratio is going down, and the uncertainty is expressed by these envelopes. So if you want to see the details, please go and consult the article. And we are estimating parameters. So here is the transmission rate, which is one of the important parameters. And so you see the oscillatory nature, which comes from the oscillatory nature of the data. However, you see that at this point, around beginning of October here, the infectivity is going down because probably of the vaccination program. And one of the things that we are all interested in is the RT, or sometimes called R0. This is the reproduction rate that we are following here. And so when the reproduction rate is below 1, the infection is waning. When it's above 1, we see a rise. And so you see that this estimated R is also oscillating, but in general, if you take the average over time, you see that we are sort of at this point, we are entering the regime beyond 1, and so it looks like, you know, the infection rate should go down, and this is indeed reflecting what we see in the area. So I'll stop with this slide, and I thank you for your attention. And if you want more about this particle filter application, please go and see this inverse problems article. And so you see all the formulas that I showed you before with the hunter and the dog in action. There are some modifications always that you need to make in order to make your particle filter to work with the particular data that we are using. But in general, this is the research in this paper is based on those formulas. And if you have questions, I'm happy to try to answer. Thanks.
Thank you, Professor Erkki Somersalo. Any questions? So I have a question, Erkki. So the thing is, so you mentioned about this data thinning, right? So yes. Where you first estimate, or estimate the position of the hunter, and then you're able to see the dog, and then based on that, then you actually remove some of the data.
Yes.
Right. But why can't we do the other way around, where first, because we know the position of the dog and the speed with which that the dog, you drew a disc around the dog, right?
Mm-hmm.
And so then based on that information, why can't I choose, let's say 10 or 20 or 1 million within that radius? So therefore the data thinning is avoided, right?
Well, the choice of those points in that disk that should be based on the previous sample. So we want to do the selection of the new points based on what we know from the previous round. And so yes, we are actually doing that. So we are selecting let's say 10,000 or 1 million points from the disk near the dog. But if you are randomizing the points, what you are doing, you are adding in that randomization, you are adding uncertainty to the position estimate of the hunter. And if that's not included in your model, then you are doing something which is deteriorating. So you get a richer sample, but that richness of the sample does not reflect your propagation model. So all this work that we are using with the survival of the fittest is really to try to avoid the thinning of the data. So we are trying to keep the sample as rich as possible and still trying to base it on the previous sample.
I see.
Does that answer? Yeah. So there are many other strategies also to do the particle filtering. So I have here a book right in front of me. It's Bayesian filtering and smoothing. I'm not advertising the book, but I'm telling you just that there are lots of different suggestions how to do this this propagation, so that you are not really sort of losing the particles, and on the other hand, you are not creating artificial diffusion.
Okay, and I also have one follow-up question. So,
yes.
Let's say you're able to track the position of the dog, and at each time, the hunter is a unique person, right? So, but each time, but where are we taking that into the model? Because let's say at each location, I see 2 or 3 persons which are very close to the dog. Then it is very likely that one among the 3 is the hunter, but at each location, the hunter remains the same.
Yes. The thing is that Bayesian methods are only telling us what we believe. And so, like I mentioned in the beginning, so that when we are talking about the sunrise, so the Bayesian models are only telling how much what we believe about, the next sunrise. So do we believe that there is going to be a sunrise? It doesn't really tell me anything about whether the sun is going to rise or not. And so in the same way, in the Bayesian sort of models, one should not think of reality, because so we know that, yes, the hunter is a single and unique person, but we have no idea where the hunter is. And so this model is not really telling anything about where the hunter actually is. It tells us what we can know about the position of the hunter. So the fact that the hunter is a unique point in the map doesn't help it at all, because we have not access to that information somehow. So Bayesian methods are really telling you what you are entitled to believe or know about, the quantity the model is talking about. I think you are unmuted now. Unmuted.
Yeah, right. Sorry. Yeah.
Yeah.
But at each step, right? Okay. So I know this doesn't address or this is, you actually addressed this point already. But at each step, if I see the same person, right, then it is more likely that that person is the hunter rather than somebody else, even though they are very close to the dog, right? But the Bayesian methods are not equipped to handle that. Is that what you're saying?
So say it again. If the Bayesian methods
are not equipped to handle such type of like uniqueness or something like that, it is like more like likelihood rather than an exact, finding out the exact location.
Yeah, so the fact that there's just one hunter is not sort of included in this model. So we are really not talking about the hunter itself. We are talking about what we can believe about the position of the hunter. So yes, we are not using the uniqueness of the solution in anywhere here. So that is correct. So
thanks. Yeah, please go ahead.
Yeah, so this somehow. I'm often citing something that Niels Bohr said about physics and quantum physics. So he said that the physics should not talk about how the nature is. It should talk about what we can know about nature. And so the Bayesian methods are very, very much in line in that. So we are not really telling what the hunter is and what the nature is. We are just trying to describe what we can know about it. Yes.
Yeah. Thanks. Any other questions? If not, thank you very much, Professor Erkki Somersalo, for taking the time and for giving this wonderful presentation. So hope to see you in person sometime very soon. So thank you very much.
Thank you, likewise, and it was a pleasure to see you all. And I will share my slides, so I will send them, and so whoever wants to peruse these later, you will have access to them. Thank you.
Okay. Thank you. Bye-bye.
Bye.